it's funny when you hear the phrase permanent human habitat.
Right, your brain just automatically looks up.
Exactly. You picture like the International Space Station or maybe some futuristic Mars colony with those, shiny geodesic domes.
Yeah, rovers kicking up red dust everywhere. We've been completely conditioned by decades of science fiction.
Oh, absolutely. And I mean, frankly, our own space race, right? To just fundamentally believe that the ultimate frontier for human habitation is, well, out there in the vacuum.
Right. It's cold, it's distant, and it's just completely removed from the biological reality of our daily lives.
But what if one of the most ambitious, like reality-altering projects for permanent human habitation isn't happening millions of miles away in the dark of space?
Which is wild to think about.
It is.
Yeah.
Because it's happening right here on Earth. Just a few hundred feet away, but straight down.
Yeah.
We are talking about building permanent, continuous underwater bases on the ocean floor.
And, before anyone rolls their eyes, this isn't some luxury getaway for a billionaire who wants to, sip martinis with manta rays.
Right. No underwater luxury hotels here. Welcome to this deep dive, by the way.
Yeah.
Today, we are taking you into a world that sounds like pure science fiction, but it's an engineering reality right now.
Very much a reality.
Yeah, so we're working from this fascinating presentation by a group called Deep Engineered, and their briefing is titled, The Zone We Can't See.
It's a great title.
It really is. So our mission today is to unpack exactly why humanity needs to establish a literal zip code on the ocean floor.
Right.
We're going to identify a highly specific, massive blind spot zone we've somehow entirely missed. And we'll break down the physics and physiology of how gaining the simple element of time underwater is the ultimate key to unlocking the ocean's secrets.
And it really requires a profound shift in perspective for you as the listener, because the ocean feels familiar to us, right?
But we swim in it, we sail on it.
We eat from it. But the presentation from Deep Engineered makes it glaringly obvious how fundamentally disconnected we actually are from understanding it.
Totally.
And that disconnection stems from one simple, immovable fact. We have just never been able to stay there.
Right. Before we get into the nuts and bolts of the underwater bases and the crazy physics of how you keep the ocean from crushing a living room, we really need to understand the fundamental problem these bases are trying to solve.
The overarching bottleneck.
Exactly. And it starts with a statistic from the source material that genuinely, it made me stop reading and just stare at the wall for a second.
It's a staggering number.
It is. The ocean is home to more than 90% of all life on Earth.
90%.
Yeah. It regulates our entire global climate system. And it produces half the oxygen you're currently breathing. Take a breath right now.
Half of that oxygen.
Half of it, generated by marine organisms. Yet, according to this presentation, we know almost nothing about the mechanisms of that life support system.
It's the great paradox of our planet, honestly. We call it Earth, but it's really planet ocean.
Yeah.
And the barrier to understanding it isn't a lack of awareness. The barrier is just the pure, unadulterated friction of access.
Okay, so the analogy that kept popping into my head while I was reviewing these notes, it's like you and I are living in this massive, sprawling, incredibly complex mansion, right?
Okay, I like this.
And the entire life support system for the mansion, so the heating, the water purification, the air filtration, it's entirely located in the basement.
Right.
And we fully acknowledge that the basement keeps us alive. We even write scientific papers about how important the basement is.
Sure, we respect the basement.
Right. But we refuse to actually walk down the stairs to check on the machinery because, well, the basement door is just way too heavy to push open.
Yeah, it's just too much effort.
Exactly. So we just sit in the living room feeling the AC kick on and off, and we're just hoping the machinery doesn't break.
That is painfully accurate. Going deep into the ocean, and more importantly, staying down there, is physically punishing and logistically astronomical, so we generally just don't do it. Or, we only do it in the most fleeting, superficial ways imaginable.
Right, but I have to play the skeptic for a second here. Because if the ocean is producing half of our oxygen and holding 90% of our planet's life, the logical question for you or me is, why haven't we thrown absolutely every resource we have at pushing that basement door open?
That's a fair question.
Right. If it's that critical, why is access still such a massive bottleneck in the 21st century?
Well, it comes down to a single variable that really governs all scientific discovery, and that's time.
Time.
Yeah, time. Until this exact moment in engineering history, humanity has completely lacked the capability to stay underwater long enough to observe it in any meaningful way. And in the scientific method, time equals data.
Time equals data. That makes a lot of sense.
Yeah. If you have continuous time to observe an ecosystem, you gather real data on how it functions. You see how it reacts to thermal stress, how organisms interact symbiotically over a full day-night cycle.
Right.
Without time, you don't have data. You just have assumptions based on fragments.
Wow. So it's not just about building a vehicle that can, survive the pressure. It's about actually maintaining a presence.
Precisely. If you can only hold your breath, whether that's literally free diving or figuratively through limited scuba tanks, for a few minutes before you have to flee back to the surface to literally survive, you aren't conducting deep ecological science. You're just taking a frantic snapshot.
A frantic snapshot. I love that phrasing. Okay, so if access and time are the core problems, where exactly are we missing out the most?
This is where it gets really interesting.
Right, because when Deep Engineered talks about this, they don't just point at a map of the Pacific and say the ocean in this broad generic sense. They zero in on a very specific, incredibly crucial band of water.
Yes.
They call it the blind spot zone.
Yeah, this is where the presentation gets extremely specific and shifts the whole paradigm of how we view marine exploration.
Okay, lay it on us.
Well, when you usually think about exploring the great, dark mysteries of the ocean, where does your mind naturally go?
I mean, I instantly picture the Mariana Trench.
Right.
Pitch black, freezing cold, immense pressure. You know those weird bioluminescent anglerfish with the glowing things on their head?
Exactly. Or you picture the abyssal plains where the Titanic rests, these extreme deep ocean environments.
Yeah, exactly.
And the extremes always capture our imagination, right?
Sure. Makes for great movies.
But Deep Engineered points out that the part of the ocean that is actually the most biologically relevant to our survival, and yet remains the absolute least studied, it lies roughly between 50 and 200 meters deep.
Okay.
That is the blind spot zone.
So roughly 160 to 650 feet down.
Exactly.
Man, reading the statistics on this specific zone, it was a genuine shock.
Mind-blowing.
Like, this narrow band holds 96% of the world's reef systems.
96%.
Yeah. And it holds over 91% of protected marine areas. And even from an archaeological standpoint, about 72% of known shipwrecks and cultural sites are there.
Right.
So almost all of the reefs, almost all the protected zones, and the vast majority of our underwater cultural heritage are literally sitting right in this relatively shallow pocket.
It is sitting right there, just off the continental shelves, and it's completely out of reach.
It's so frustrating.
It is. And in marine biology, this area roughly corresponds to what we call the transition from the epipelagic zone, that's the sunlit top layer, down into the mesophotic zone.
Mesophotic?
Yes, which literally translates to middle light.
Oh, interesting.
And there is a very specific biological reason why this mesophotic zone is the absolute jackpot of the ocean. It all comes down to the physics of light attenuation.
Okay, let's dig into that physics, because I want you to understand this.
Yeah.
Why is this 50 to 200 meter band so special? What happens to the light?
Well, as sunlight hits the ocean surface, the water immediately begins absorbing and scattering the light waves.
Right. Red, yellow, and orange wavelengths are absorbed very quickly, usually within just the first 10 to 20 meters.
Oh, wait, is that why, if you get a cut underwater while scuba diving, the blood looks green?
Yes, exactly. Because the red light doesn't penetrate that deep, so there's no red light to reflect off the blood.
Oh, wow. Okay. That makes so much sense now.
Right. But blue and green wavelengths, they have higher energy, so they penetrate much deeper. And in that 50 to 200 meter depth range, you have this highly filtered, very dim blue light.
Like twilight.
Exactly like twilight. It's not much, but it is just enough penetrating sunlight to enable photosynthesis.
Wait, really? Even that far down?
Yes. Plants and algae can still grow, even though it's practically twilight.
That is wild.
And the organisms that live there have adapted incredibly to maximize that scarce resource.
How so?
Well, shallow water corals, they might look like branching antlers, right? You've seen those.
Yeah, like typical coral reefs.
But mesophotic corals, they often grow in these massive, flat, plate-like structures.
Oh, to act like solar panels.
Exactly, to catch every single stray photon of blue light drifting down from above.
That is so cool.
And where you have photosynthesis, life doesn't just exist, it explodes.
Right, because you have the food source.
You have the foundational building blocks for complex food webs. The presentation uses a brilliant phrase here. They call it Ecosystems stack on ecosystems.
I love that imagery. Stacking ecosystems. It totally dispels that myth of the ocean floor as just like a flat expanse of sand.
Right. It is a dense, vertical metropolis down there.
Yeah.
You have the coral structures creating the physical architecture like the skyscrapers, essentially.
Okay.
Then you have the microorganisms and zooxanthellae feeding on the light, then small pelagic fish feeding on them, then benthic creatures crawling all through the architecture.
Like crabs and stuff.
Right, and then larger apex predators patrolling the perimeter. The presence of just enough sunlight combined with the stabilizing depth that actually protects these reefs from surface storms and extreme temperature fluctuations. Oh, because they're deep enough to not get battered by hurricanes.
Precisely. It creates a biological density that is almost unparalleled anywhere else on the planet.
Which honestly just makes it all the more infuriating.
It really does.
Like, we have this biological jackpot literally just off the coasts of our continents, and yet it's our blind spot.
Yeah.
So, okay, if this mesophotic zone is bursting with life, shipwrecks, complex reef cities, why is it a blind spot? I mean, we've had scuba diving since, what, Jacques Cousteau helped invent the aqualung in the 1940s?
43, yeah.
Right. And we have nuclear submarines that can stay underwater for months on end. Why haven't our tools solved this yet?
Well, this brings us to what might be the most fascinating logistical paradox of ocean exploration.
Okay.
We're dealing with a massive technological gap. That 50 to 200 meter mark is a structural dead zone for our current engineering.
Okay, here's how I tried to map this out while reading the source material, because it took me a second to grasp.
Sure.
It's like we have bicycles, right, which are fantastic for going down the street to the grocery store.
Okay. And we have massive commercial jetliners, which are incredible for flying across the Atlantic Ocean.
Yep.
But nobody ever bothered to invent a car for the middle distance.
Exactly.
We are completely bypassing the town right next door because we can't physically pedal a bike there, and we obviously can't land the 747 in their town square.
That maps perfectly to the reality of marine technology. Let's break down the bicycles and the jetliners of the ocean so you can understand why the car doesn't exist.
Okay, let's do it. Let's start with the bikes.
Up to about 50 meters, standard scuba diving is safe and highly effective.
Right.
A marine biologist can strap on a tank of compressed air, swim down to 20 meters, spend a reasonable amount of time observing a shallow reef, and swim back to the surface without immense physiological danger or requiring some massive support crew.
Right. The bicycles. Cheap, accessible, effective for short distances.
Exactly. Now look at the other extreme.
The 747s.
Right. If you want to go really deep past 200 meters down into the thousands of meters where the Titanic sits or where those hydrothermal vents are, large, heavy submersibles start to make economic sense. You are investing tens of millions of dollars into exploring the abyssal plains, so you build a massive, heavily engineered titanium sphere to protect the occupants from the crushing pressure.
Okay, so that's your jetliner.
Yes, but the band in between that 50 to 200 meter mesophotic zone, where 96% of the reefs are, is a trap.
A trap.
It is a complete trap. It is too deep for scuba divers to operate sustainably, and yet it is too shallow. And it requires far too much fine motor interaction to justify the astronomical costs of deploying deep-sea submersibles.
Okay, the deep engineered notes use that specific phrase, operate sustainably, when talking about scuba divers in this zone.
Yes.
We need to unpack what that actually means in physiological terms. Like, why can't a highly trained scuba diver just swim down to 150 meters, take some notes on a clipboard, and swim back up?
Because human physiology violently clashes with hydrostatic pressure.
Violently. Great word.
It's true. For every 10 meters you descend into the ocean, the weight of the water above you adds another full atmosphere of pressure.
Okay. At the surface, you are at 1 atmosphere. At 100 meters down, you are experiencing 11 atmospheres of pressure.
11 times the normal weight of the air.
That is 11 times the weight of the air we normally feel pressing on every square inch of your body.
Jeez. But our bodies are mostly water, right? So we don't just, crush like a tin can.
Correct. The fluids and solids in our bodies are mostly incompressible, but the gases inside our bodies, specifically the gases we are breathing from a scuba tank, are highly compressible.
Okay.
This is governed by Boyle's law, which states that the volume of a gas decreases as pressure increases.
Right, physics class is coming back to me.
So to keep your lungs from just collapsing at 100 meters, the scuba regulator has to deliver air at that exact same crushing pressure of 11 atmospheres.
Oh, wow.
Yes, and breathing gas at that pressure introduces entirely new biological terrors.
Terrors is the right word. Lay it on me. What happens?
Well, when you breathe gases at that extreme pressure, their chemical behavior in your bloodstream changes completely.
Really? Just because of the pressure?
Just because of the pressure. Take nitrogen, which makes up about 78% of the air we breathe normally.
Right.
Under high pressure, nitrogen becomes intensely narcotic. It literally acts like an anesthetic.
Wait, like you get drugged?
Exactly. Divers call it the martini effect or nitrogen narcosis.
The martini effect.
Yeah. At 50 meters, a diver might feel mildly drunk. At 100 meters, if they were breathing regular air, a diver would be so profoundly incapacitated they might forget which way is up, or simply take the regulator out of their mouth because they think they don't need it.
Oh my God. That is terrifying.
It gets worse. Even oxygen becomes highly toxic to the central nervous system at those partial pressures. It causes violent seizures.
Wait, oxygen becomes toxic?
Yes. Toxicity is a huge risk in deep diving.
So to dive into the blind spot zone, you can't even use regular air?
No, absolutely not. You have to breathe custom, highly specialized gas mixtures.
Like what?
Like trimix, where you replace that narcotic nitrogen with helium and you drastically reduce the oxygen content so it doesn't poison you.
Okay, so you're breathing helium and a tiny bit of oxygen.
Right. But that only solves the poisoning and the narcosis. It doesn't solve the most famous danger of diving.
Decompression sickness. The bends.
Exactly, the bends. The gas mix actually makes the decompression math much more complicated.
Okay, let's use a mechanistic metaphor to understand decompression sickness because this is crucial.
Let's do it. Think of the human bloodstream under pressure like a sealed, clear bottle of carbonated soda.
Okay, I can picture that.
When the bottle is sealed and under pressure, the liquid looks perfectly clear, right? The carbon dioxide gas is fully dissolved into the liquid.
Right, you can't see the bubbles at all.
But what happens if you unscrew that cap rapidly?
The pressure drops instantly, and all that dissolved gas violently comes at a solution. Like the soda fizzes and explodes all over your kitchen.
Exactly. And if that happens in a human body,
Oh, man.
the inert gases that your tissues absorbed while you were under pressure at 150 meters, they suddenly turn into physical bubbles in your bloodstream, inside your joints, and in your spinal cord.
Jeez.
It causes agonizing pain, paralysis, or even death.
So to prevent this, a diver just can't swim straight up to the surface.
No, they must unscrew the cap incredibly slowly. They ascend a few meters, stop, and wait for their body to slowly off-gas through their breathing.
Right, they have to literally sit there and breathe the bubbles out.
Yes, which creates the ultimate bottleneck.
Okay, put this into perspective for us. How long does that take?
If a diver spends just 15 minutes doing actual research at 150 meters, they might need to spend hours, literally hours, hanging onto a rope in the open ocean, slowly ascending to the surface just to prevent their blood from boiling with bubbles.
Wow.
The physical toll of the cold and the pressure, the economic cost of the specialized trimix gas and the support boats, and the sheer logistical nightmare. It creates an impenetrable barrier.
So you spend hours of suffering just to get minutes of observation.
Exactly. It is the exact opposite of sustainable science.
Right. Okay, so because we don't have the right tools, how have we been studying this 50 to 200 meter zone up until now? Because, marine biologists do exist. There are papers written on mesophotic reefs. We know they are there.
They exist, but the research is conducted through what the deep presentation very critically, and I think accurately, calls drive-by research.
Drive-by research. Wow, it sounds fundamentally inadequate for understanding a complex ecosystem.
It is entirely inadequate. Because of the extreme physiological limits of decompression we just discussed, the blind spot zone is currently only visited through brief drops by highly experienced technical divers or remote-controlled cameras.
Okay.
We are talking about bottom times measured in single-digit minutes.
The source material uses a really evocative analogy to explain the flaw in this method, right?
Yes, the helicopter analogy.
Yeah. They compare drive-by research to trying to understand a major metropolis by flying over it once a year.
Right.
Like, imagine you were a sociologist or an urban planner, and your job is to understand how New York City functions. But you are only allowed to fly over Manhattan in a helicopter for 3 minutes, once a year.
You will gather some data, certainly.
Sure, yeah. You'll see the buildings. You'll note that the Empire State Building hasn't moved since last year.
Right.
You might catch a glimpse of a traffic jam on the Brooklyn Bridge from above, but you don't see the culture.
No.
You don't hear the noise of the traffic. You have zero understanding of the complex rhythm of the subway system or how the vendors interact with pedestrians on the sidewalks or, what the air smells like after a rainstorm.
You miss the actual life.
Exactly. You completely miss the actual life of the city. You miss everything that makes it a dynamic, living system rather than just a collection of concrete blocks.
That captures exactly what is lost when we conduct drive-by research on a mesophotic coral reef. A stacking ecosystem is not a static painting. It is immensely dynamic.
Give us an example. Let's ground this in a specific biological scenario.
Okay, think about coral spawning.
Okay.
Many species of coral reproduce by releasing eggs and sperm into the water column simultaneously.
Oh, like a massive underwater snowstorm. I've seen videos of that.
Exactly. It is a massive, highly synchronized event that provides the foundation for the entire reef's survival.
But it doesn't happen all day long, right?
No, it is often tied to incredibly specific environmental triggers, like the exact cycle of the moon, the specific water temperature, and it often occurs for just a 20-minute window once a year.
Oh, wow. Once a year for 20 minutes.
Yes. Now imagine a technical diver is down there trying to observe this, but their bottom time dictates they must begin their 3-hour decompression ascent at 10:00 p.m.
Okay.
And the coral decides to spawn at 10:15 p.m.
Oh, no. So they miss it entirely.
They miss the most important biological event of the year because the ticking clock of their own physiology forced them to leave.
That is tragic from a scientific perspective.
It is. And furthermore, to truly understand complex symbiotic relationships, observation requires stillness.
Stillness?
Yes. It requires a quiet presence. You have to become part of the background noise so the ecosystem stops reacting to you and goes back to acting naturally.
Right, if you walk into a forest, all the birds stop singing.
Exactly. You have to sit still for an hour before the forest ignores you. Drive-by research completely prevents that.
Because you're in a rush.
Right. A technical diver drops in, covered in heavy equipment, making a ton of bubbles and noise, desperately rushes to grab a few physical samples or snap a dozen photos before their decompression limit hits, and then they flee back to the surface. It is not observation. It is an ambush.
An ambush? Wow.
It's just a snapshot of a startled ecosystem.
Okay, so the problem is clearly defined for us now. Reef visits are failing us. We are blind to the most vital part of the ocean because the physics of our own bodies won't let us stay there.
Right.
So the logical step, and this is where we transition from the problem into the absolutely mind-bending engineering solution, is to stop visiting and start staying.
Which brings us to the core mission of Deep Engineered.
Yes.
They are building the physical infrastructure for a permanent, continuous human presence on the ocean floor, placed directly into that 50 to 200 meter blind spot zone.
Let's talk about the mechanics of what these bases actually are, because the imagery and the engineering in these notes are stunning.
It really is beautiful engineering.
Right. We aren't talking about a glorified submarine here. We are talking about modular habitats placed deep underwater where teams of people can live, conduct lab work, sleep, and eat for days or weeks at a time without ever needing to resurface.
Yes.
And the notes mention that internally, the environment is designed to feel almost normal.
What does that mean? Well, you are still sitting under potentially hundreds of feet of crushing hydrostatic pressure. The engineering required to build a hull that simply won't implode is monumental.
Sure.
But internally, the environment is climate-controlled, dry, and optimized for human psychological and physical comfort. You aren't huddled in a cold, damp tube.
Okay, but the feature that absolutely hooked me, like the piece of engineering I cannot stop thinking about, is the moon pool.
Ah, yes, the moon pool.
It is so cool.
It is a classic feature of advanced underwater habitats, actually. It traces its roots back to early experiments like Jacques Cousteau's conch shelf habitats in the 1960s or NOAA's Aquarius Reef Base.
Right.
But the application in the deep habitats is revolutionary.
Okay, so for you listening, imagine walking into your living room or your laboratory, and instead of a solid floor in one section, there is just an open pool of water.
Just right there in the floor.
Right. It is a direct, open gateway to the ocean outside. So the immediate question anyone asks is, why doesn't the water instantly flood into the room and drown everyone?
It's a brilliant application of physics. To understand how a moon pool works, think about taking an empty drinking glass, turning it upside down, and pushing it straight down into a bucket of water.
Okay, I've definitely done this as a kid in the bathtub.
Exactly. The water doesn't fill the glass because the air trapped inside has nowhere to go.
Right.
As you push the glass deeper, the water pressure compresses the air slightly, pushing the water line up a little bit into the rim of the glass, but the top of the glass remains completely dry.
Because the air pressure inside pushes back against the water pressure outside.
Exactly. In the deep habitat, the internal atmospheric pressure is artificially pumped up to perfectly match the hydrostatic pressure of the ocean outside at that specific depth.
Oh, wow.
Because the pressures are absolutely equalized, the ocean simply stops at the opening of the moon pool.
It just sits there.
It sits there like a perfectly flat liquid trap door.
That is wild.
So scientists can sit on the edge of it in dry clothes, slip on their dive gear, drop directly into the mesophotic zone to do their work, and then simply climb back out into a warm, dry laboratory.
Okay, but wait. This completely rewrites the logistical rulebook we just talked about.
Yes.
Like, what about the hours of agonizing decompression hanging on a rope?
The habitat eliminates that entirely.
Entirely.
Through a physiological principle called saturation diving. This is the foundational science making this entire endeavor possible.
Okay, let's break down saturation diving, because the source material claims these habitats act like time machines.
Yes, time machines.
And turning years of work into days. I'll be honest, I initially thought that was just marketing hyperbole.
It is not hyperbole. It is a mathematical reality based on how human tissue absorbs gas.
Okay, walk me through it.
Remember how we discussed inert gases dissolving into the diver's bloodstream under pressure, like the carbonation in a soda bottle?
Yes, and ascending too fast makes the bubbles explode out.
All right. In traditional scuba diving, the longer you stay down, the more gas your tissues absorb, which means the longer your decompression ascent takes.
Okay, that makes sense. More gas equals more time needed to off-gas.
Exactly. But in the 1950s and 60s, a visionary naval medical officer named George F. Bond proved a radical theory.
George F. Bond.
Yes. He discovered that the human body eventually reaches a point of absolute saturation.
Meaning what?
After about 24 hours under pressure, your tissues have absorbed all the inert gas they can possibly hold.
They are full.
They are completely full. They become completely saturated.
No.
And here is the magic of saturation diving. Once your body is fully saturated, your decompression time becomes a fixed mathematical constant.
Wait, really?
Yes. It does not matter if you stay at that depth for one more day, 1 week, or one entire month. The decompression penalty stops accumulating.
Oh, wow. So if a scientist is living inside the deep habitat at 100 meters, their body reaches full saturation on day 1.
Yes. Because the air inside the habitat is pressurized to match the 100-meter depth, the scientist's body is fully saturated.
Okay.
This means they can slip out of the moon pool, spend 6 uninterrupted hours observing a coral spawning event, and then swim back into the habitat.
Yeah, because the habitat is at the exact same pressure as the water outside.
They experience zero pressure change.
Therefore, they require zero decompression.
Exactly. They can take off their gear, take a hot shower, eat dinner, and go to sleep. And they can wake up and do it all again the next day.
Because they only have to pay the decompression penalty once.
Exactly. At the very end of their weeks-long mission, the entire habitat's internal pressure is slowly, safely brought back to surface pressure over a period of days while they just relax inside, or they are transferred to a decompression chamber on a ship.
That is unbelievable. Let's run the math on that time machine claim now, just to really hammer this home.
Okay, let's do the math.
So, a highly trained technical surface diver doing drive-by research might get, 15 minutes of bottom time at 100 meters?
Right.
And maybe they can only do that once a day due to the exhausting 3-hour decompression.
Yeah.
So factoring in weather delays, ocean currents, and sheer physical exhaustion, a 2-week surface expedition might yield just 3 or 4 hours of total fragmented observation time.
If they're lucky. Now put that same scientist inside a deep habitat.
Yeah.
They drop out of the moon pool and work for 6 or 8 hours a day, every single day, completely unaffected by surface weather or waves.
Because they are already below the weather.
Right. So in just 3 days, they have accumulated more continuous, high-quality, immersive observation time than they would have in an entire decade of surface-based expeditions.
Wow. It quite literally is a geometric leap in data collection.
It really is.
By eliminating the biological toll of constantly resurfacing, they are buying back scientific time at an exponential rate.
Yes.
The sheer volume of data, the ability to observe the stillness, to see the whole city instead of just flying over it, it fundamentally changes the nature of what marine biology can be.
It shifts the entire discipline from brief, frantic extraction to continuous, immersive understanding.
Okay, so we have the habitat. We understand the physics of the moon tool and the physiological magic of saturation diving.
Right.
That leads us to the final and perhaps most philosophical piece of this puzzle.
Who actually goes inside?
Exactly. Who goes inside this habitat?
Yeah.
The deep engineered notes are very clear on the makeup of the team. It is a diverse coalition of engineers, scientists, aquanauts, and explorers from varied disciplines.
Right. It's a very multidisciplinary approach.
And they share a singular core belief, which the presentation highlights. They believe the most important discoveries on Earth are still beneath the waves, waiting to be found.
Which is absolutely true.
But they insist that to find these discoveries, we need more than just remote-controlled cameras. We need human beings physically in the water.
Yes, human presence is non-negotiable for them.
Now, I have to challenge this premise.
Yeah.
Because I guarantee you listening to this right now are thinking the exact same thing I was.
Okay, what's the challenge?
We live in the golden age of artificial intelligence and robotics.
True.
We have autonomous swimming drones. We have rovers driving across the surface of Mars right now, beaming back high-resolution panoramas to scientists sitting in air-conditioned offices in California.
The two.
So why in the world are we risking fragile human lives, subjecting them to immense hydrostatic pressure and complex saturation physiology, just to look at a reef?
It seems counterintuitive.
Couldn't we just drop a network of 2047 4K cameras down there, deploy some ROVs, remotely operated vehicles, and do the exact same science without the risk?
This raises an incredibly vital debate about the fundamental philosophy of exploration.
Right.
It is the tension between automated data collection and human intuition. Deep Engineered takes a very firm stance on this, and it comes down to understanding the limitations of machines in highly chaotic environments.
Because, I mean, a robot doesn't need to decompress.
No.
It doesn't get nitrogen narcosis.
True. An RV doesn't get cold, it doesn't need to eat, and it can stay down infinitely as long as it has power. But what does a robot actually do?
It takes pictures.
Right. It executes a pre-programmed mission. It takes a picture of a specific grid quadrant. It records ambient water temperature. It gathers discrete data points based on what its human operator told it to look for.
Okay, so it only sees what you tell it to see.
Exactly. And when you are operating an ROV from a surface ship, you are essentially looking at the ocean through a narrow straw.
Through a straw, I like that.
You're dealing with monitor latency, and you lack any true spatial awareness. You can't feel the current shift. You can't hear the ambient noise in stereo.
So you are capturing the snapshots we talked about earlier,
Right.
just robotic ones instead of diver ones.
Yes. But an environment as deeply complex as a stacking mesophotic ecosystem isn't just a collection of discrete data points.
No.
It is a fluid, chaotic, entirely unpredictable web of biological interactions. While an AI drone can take a flawless, color-corrected picture of a coral head,
A human scientist can do what?
a human scientist suspended physically in the water possesses something that no machine learning algorithm currently has.
Which is?
Peripheral intuition.
Peripheral intuition. I want to explore that concept deeply because that sounds important. What does that actually look like in practice?
Imagine a scientist swimming out of the moon pool. Their specific funded mission for the day is to measure the growth rate of a particular plate coral.
Okay, a very standard mission.
But as they're swimming toward the coral out of the corner of their eye, they notice a small fish behaving erratically. Or their binaural hearing picks up a strange clicking sound echoing off the reef structure behind them. They notice a shadow or a movement pattern that just doesn't quite fit the baseline topography they've been immersed in for the last week.
They sense an anomaly.
Exactly. A human can synthesize that massive, chaotic stream of sensory context on the fly. The human brain naturally asks, wait, why is that species here at this time of day? It shouldn't be here. What is it interacting with?
Right.
And then, using their peripheral intuition, they can instantly pivot their entire research focus in real time to investigate that anomaly.
Oh.
They might discover an entirely unknown symbiotic relationship between that fish and a newly discovered species of sponge.
Wall the robot.
An ROV flies right past that sponge because its camera was pointed straight ahead at the coral and its algorithm simply wasn't programmed to look for a fish swimming erratically.
That makes so much sense. So a robot records the expected, but a human explores the unexpected.
Exploration, at its core, requires curiosity.
Curiosity, yeah.
It requires the emotional and intellectual capacity to be surprised. and the autonomy to instantly act on that surprise. If we truly believe that the most critical discoveries regarding our planet's life support systems are still down there,
We can't just rely on cameras.
we cannot rely solely on automated recording devices looking through a straw. We need the human mind, with all its chaotic, brilliant, intuitive leaps, situated physically within the environment. Humans are the ultimate anomaly detection engines.
Humans are the ultimate anomaly detection engines. That is such a powerful way to frame it. You can't program a drone to have an aha moment.
You really can't.
And when you are dealing with an environment that holds 90% of the life on Earth, and a specific blind spot zone that holds 96% of the reef systems that we barely comprehend, we desperately need those aha moments to figure out how the basement machinery works before it breaks down.
Exactly. We need presence.
Okay, let's pull all of this together to see the complete picture of what we've covered today.
It's been a journey.
It really has. We started by confronting the massive existential bottleneck of access, the crushing physics that kept the basement door closed, leaving us completely blind to the very ocean that produces half our oxygen.
Right. And we identified exactly where that most critical blind spot is, the 50 to 200 meter mesophotic transition zone.
Jackpot.
The biological jackpot, where highly filtered blue sunlight still penetrates, allowing complex ecosystems to stack upon each other, holding the vast majority of our reefs and underwater cultural heritage.
Yeah, and we looked at the infuriating technological gap, too. The reality that this vibrant zone sits exactly in the middle of our engineering capabilities.
The missing middle distance car.
Exactly. Too deep and dangerous for sustainable scuba diving due to hydrostatic pressure and decompression sickness, but requiring far too much intimate observation to justify deep-sea submersibles.
A gap that forced us into decades of useless drive-by research, trying to understand a bustling, dynamic underwater metropolis by flying over it for a few minutes a year.
But then we explored the engineered solution: permanent underwater habitats utilizing the physics of moon pools and the incredible physiological reality of saturation diving.
Time machines.
The time machines, eliminating the decompression penalty and turning years of grueling fragmented surface work into days of continuous immersive observation, allowing human peripheral intuition to finally operate at the speed of true discovery.
It is a profound shift in how we approach our own planet.
It really is. We're finally building the tools to push the basement door open and actually stay down there.
We are.
But before we wrap up, I want to leave you, the listener, with a final lingering idea to mull over.
Okay.
We spent this time breaking down the how and the why, based on the engineering and biology of Deep's presentation. But let's look past the immediate horizon for a second.
I like where this is going.
If we successfully establish a permanent human presence in this 50 to 200 meter blind spot zone, if the engineering is perfected, these habitats become common, and we begin to truly unlock the secrets of these stacking ecosystems. How will this alter our fundamental definition of human civilization?
That is the ultimate question.
Right. If humanity proves we can safely and productively live under the crushing pressure of the mesophotic zone, will we eventually view the ocean floor not as a dark alien frontier that we occasionally and bravely visit,
but simply as a permanent, active neighborhood of human life?
Yes, a neighborhood.
And if the ocean floor fundamentally shifts in our collective psychology from being a distant other to becoming an extension of our own neighborhood, how does that change our inherent responsibility to protect it?
Ooh, that is a heavy thought.
Because it is one thing to vaguely pollute a vast, abstract, unseen ocean. It is entirely another thing to pollute your own backyard.
The basement door is finally opening and the lights are turning on. The question isn't just what we will find down there. The question is, who do we become once we move in?